Welcome to the O-Level Chemistry lecture series. So once again, notes and tutorials, if you do not have them, please obtain them from the photocopy shop. There are some other recommended additional practices: 10-year series, your MRs, class tests, end of your papers, and other schools' prelim papers 1 to 3 will be provided for you. There are other external assessment books which you may consider, so go ahead, find more stuff to practice on. So let's start with today's lesson. Today's lesson is on speed of reaction. So please make sure you have ready on hand the notes on speed of reaction, as I'll be delivering it through PowerPoint, which will closely mirror the flow of the notes. So let's have a very quick overview. Rate of reaction. Some rates can be fast, some rates can be slow, some rates can be really slow. Let's take for example rusting of a iron nail. It could be a very slow reaction or it could be a very fast reaction depending on the conditions. Later on we will cover more on the conditions as well. Another reaction that is very fast, which you would probably have seen before in the lab, is probably the reaction between calcium carbonate and dilute sulfuric acid. So as you put the carbonate into the acid, the carbonate slowly dissolves, very quickly dissolves, and you see a lot of gas, which is called effervescence. See a lot of fizzing, and eventually the calcium carbonate pieces will disappear. So that is what we could consider a moderately fast reaction. An explosion will be called a very fast reaction. So why is an explosion so dangerous? It's because the reaction is so fast that so much energy is released, and this amount of energy released causes a tremendous amount of damage. So now let's move on into the pre-learning section. There are 3 ways of measuring the rate of a reaction. You notice that I do not use the word speed of a reaction, even though the topic is speed of reaction, because technically speed, you can't really measure speed. Speed is not a vector quantity. Rate, rather, it's defined as per unit time, the change of something per unit time. So how do we measure the rate of a reaction? There are various ways we can go about doing this. So one of them is to measure the amount of product formed. So for example, you were to use a conical flask and you have some acid inside, H2SO4, and we add in calcium carbonate. So we will have this reaction happening. CO3 plus H2SO4, we will get calcium sulfate. Salt plus water plus carbon dioxide. Is the equation balanced? Yes, it is. So we will get carbon dioxide gas produced. And if we were to attach a gas syringe to this setup over here, like this, we will be able to measure the volume of gas evolved. And if we were to use a stopwatch at the same time, we will be able to find out how much gas was evolved per unit time. Probably you could take a reading every 5 seconds, and the volume of gas evolved can be plotted into a graph. Later on we will go into the graphing a little bit more. Another way of measuring the rate of reaction is to find out how much reactant was used up. So for example, let's go back to the previous case. I were to have some acid inside, and I were to add in calcium carbonate, and then I place this entire setup on top of a weighing scale. So let's say the whole setup weighs 100 grams. As the reaction proceeds and as calcium carbonate and H2SO4 is used up and CO2 is evolved and released into the atmosphere, the mass reading will decrease. So as the mass reading decreases, we will be able to find out how fast the reaction proceeded, provided we have a stopwatch again. So rate of reaction. Rate means per unit time, and the time is measured with the stopwatch. Another way we can measure the rate of reaction would be to see what changes occur during the reaction. So for example, color or conductivity. So maybe we have a reaction which is initially, the reaction mixture is initially colorless, and as the reaction proceeds, more and more substance is formed, and we can measure the changes in color with a calorimeter. Conductivity wise, maybe at the end of the day we have a precipitation reaction going on. So let's say we have silver nitrate plus HCl, we get AgCl plus HNO3. So we know that AgCl is a solid. So initially we have 1, 2, 3, 4 ions. At the end of the day we have 1, 2 ions. So conductivity will decrease. So we can measure the change in conductivity against time, and we will be able to determine the rate of the reaction. So as I earlier mentioned, we can use acid carbonate, measure the rate of evolution of carbon dioxide to determine the rate of a reaction. And this is what I was saying just now. We have a graph which can be plotted against time. So at 0.5 minutes we have 10 cm cube. At 1 minute we have about 35 cm cube. Oh, sorry, 0.5 we have about 15 cm cube. At 1 we have about 35 cm cube. So as time goes on, you get more and more gas produced. Eventually you see that it becomes flat. This is a plateau. Why does it become flat? Because the reactants have been used up. So once one of the reactants have been used up, we call it the limiting reactant. If you recall, limiting reactant. So once the limiting reactant is used up, a reaction stops, no more gas is produced, and we have a flat line or a plateau. In this case, this flat line corresponds to 70 cm cube of gas. You notice that the graph becomes less, and the gradient of the graph becomes less and less steep. So if I were to draw a gradient here, this would be my gradient. If I were to draw a gradient here, this would be my gradient. And over here, this is gradient 0. So you notice that the gradient gradually decreases. Why is that so? We will cover this later on in this topic. So as earlier mentioned, we can measure the change in mass of a reaction mixture by putting the whole setup onto a weighing scale, and we will get a graph similar to this shown here. You notice the graph shows that the mass is decreasing. Again, initially the gradient is the steepest. Steepest gradient means that the rate of reaction is the fastest. So as time progresses, the gradient becomes more and more gentle until it reaches 0. Why 0? Because there is no more reactants left. One or more of the reactants has been used up. No more gas is lost. So there's no more change in mass. So maybe let's say the final mass is 50 grams. Let's say this is 50 grams. Right? Okay. So attempt pre-check 1. This one is a pretty simple pre-check. So we can pause the video now to attempt the checkpoint. Continue with the video once you are done. Okay, so in pre-check 1, you are supposed to draw two graphs on the axis below to show a fast and a slow reaction between calcium carbonate and dilute hydrochloric acid. The volume of gas evolved is measured against time. So how do you draw the two different graphs? So one is a fast reaction, one is a slow reaction. So let's say this is the fast reaction. Just draw one sampling for a fast reaction. Make sure you take note that as your graph goes upwards, the gradient has to gradually decrease until it reaches 0, flat line at the top of the plateau. So this is the fast reaction. So what about the slow reaction? The slow reaction would be below. Make sure you draw the graph below the fast reaction. But take note, at the top of it, the plateau must meet. They must meet because this is the same reaction taking place. It's just fast or slow. So why can the reaction be fast or slow even though you are using the same reactants? Later on in this topic, we will cover a little bit more on the 4 factors which affect the rate of a reaction. So now, alright, let's move on to the next part of speed of reaction. But before we progress on to the next part, we must first understand how a reaction takes place. So there's this theory which we call the collision theory. So let's take for example this. I have two reactant molecules here, two reactant particles here, and they are free by themselves first. So imagine during a reaction, the first thing that must happen is that the two reactant particles must meet. So collision theory states that for two or more particles to react to form a product, they must first meet. So they must first meet and collide. When they collide, they must do so with sufficient energy to overcome activation energy. So this is a collision. Imagine there's not enough energy to overcome activation energy. They will collide and then they will break apart. So the second thing that collision theory states is that they must collide with the correct orientation. So imagine if they were to collide this way. This is the incorrect orientation, there would be no reaction. So let's say that they collide with sufficient energy to overcome activation energy and the correct orientation. They collide this way, they will form the product successfully. So this is the product being formed. So collision theory states that, let's do a quick recap. For a reaction to take place, the reacting particles must collide first with sufficient energy to overcome activation energy, and they must collide with the correct orientation. Okay, so as highlighted in the demonstration earlier, for something to react, they must collide. They must first collide, and they must collide with sufficient energy to overcome activation energy, and they must collide with the correct orientation. So if we want a reaction to proceed faster, we will need to increase the number of collisions per unit time, because doing so will allow us to have a greater probability of having the reactant particles collide with the correct orientation, and it will also allow a greater chance of particles colliding with sufficient energy. So let's move on to the factors which affect the speed of reaction. There are four main factors here, with one extra one, which is a catalyst. The catalyst is an additional factor which affects the speed of reaction. In industry, the main ones which are used is size of particles, pressure, temperature, and presence of the catalyst. So let's move on to the first one, the concentration of reactants. So what happens when we increase the concentration of a reactant? So earlier we mentioned that for a reaction to take place, the first thing that must happen is that the particles must collide. So if I have particles colliding, and if I have more particles per unit volume colliding, so imagine that this is a beaker and these are my reactants. This is the same beaker, same size, and this is the number of reactant particles per unit volume. So you notice that there's a higher chance for particles to collide when it is more concentrated versus when it is more dilute. So when I have more reactant particles per unit volume, the frequency of collision increases. Take note, a collision does not mean that a reaction will take place, but the frequency, if the frequency increases, it means that I have a higher chance of the reaction taking place. So with many more particles colliding and a higher chance of a reaction taking place, at the end of the day, to sum it all up, it means that the speed of the chemical reaction will increase. Alright? So now let's move on to checkpoint 1. Pause the video now to attempt the checkpoint. Continue with the video once you are done. So in checkpoint 1, we have two containers. We have two conical flasks. They both contain some magnesium ribbon, the same mass of magnesium ribbon, but in the first one we have 1 mole per dm cube of HCl, and in the second one we have 2 moles per dm cube HCl. So both cases contain HCl. So if we were to draw the rate of evolution of gas from these two containers, these two conical flasks, how would they look like? So first of all, let's analyze the question a little bit more in depth. Notice that the volume is different. The concentration of the acids are different. One is 1, one is 2. It means that this setup is actually more. This setup has a more concentrated acid, and as a result, because concentration increases, it means that the rate of reaction will be faster. But does it mean that because I have a more concentrated acid, that I will actually get more hydrogen gas evolved? No, because the question states that the acid is in excess. HCl is in excess. Same for here, HCl is in excess. So during the reaction between magnesium plus HCl, we would get MgCl2 plus hydrogen gas. So because HCl is in excess, it means that magnesium is a limiting reagent, so no matter how much extra HCl we add, we will still have the same volume of H2 produced. So the only difference is how fast the gas is produced. So if you were to draw out the reaction, draw out the graphs with 2 mole per dm cube HCl, if this is the graph, the one with 1 mole per dm cube HCl would be below it, because you notice that the plateau is much faster. We hit the plateau much faster for the concentrated acid. We hit it much slower for the one with the more dilute acid. And the gradient tells us about the rate of reaction as well. This is a steeper gradient, this is a more gentle gradient. So the steeper gradient tells us that the rate of reaction is actually faster. Right? So now let's move on to the next factor which affects the speed of reaction, which is the size of the reacting particles. So imagine this. If you recall earlier, for something to react, for a reaction to take place, the particles must collide. So if you were to observe the first diagram over here, I have a huge lump of solid, and I have many other particles, reacting particles, trying to collide with this solid reactant here. Versus this case, when I have many small solid particles, and I have an equal number of reactants in liquid state trying to collide, at the end of the day, it means that for this reaction mixture here, there is a higher chance for collision to take place. Why? Because there's a greater surface area to volume ratio. So if I expose more surface for the reactant particles to collide, it means that I can increase the number of collisions per unit time, and as a result, I increase the probability of an effective collision. So at the end of the day, the speed of the reaction will increase. So if you have read in the papers or online on explosions happening at places where flour is stored, so why do explosions take place in these places? It's because flour is powder form, and being a powder, it has a huge surface area to volume ratio, and a small spark will easily ignite the flour, and it will burn in air, and because it's so fine and the surface area to volume ratio is so huge, it will burn very quickly, explosively, as a matter of fact, and it will cause a tremendous explosion. So now let's move on to checkpoint 2. Pause the video now to attempt the checkpoint. Continue the video once you are done. So in this question, you have 100 cm cube of 1 mole per dm cube dilute hydrochloric acid reacting with 50 grams of marble. So what is marble? Marble is calcium carbonate. So this is a carbonate acid reaction which will give you a salt, water and carbon dioxide. So in flask 1, the marble was broken into small chips. In flask 2, the marble was a single piece weighing 50 grams. So small chips versus single piece, surface area to volume ratio so comes into play. So small chips, larger surface area to volume ratio, you would expect the reaction to be faster compared to the one containing the single piece. So now, before we begin drawing the graph, observe the question, and you will notice that there's sufficient information given for you to calculate the volume of gas produced. So what is the gas produced? It is carbon dioxide. So how do we go about calculating the volume of gas produced? First of all, we must write the equation. A balanced equation, carbonate plus HCl gives me CaCl2 plus water plus carbon dioxide. So this is the gas concerned. And we have enough information to calculate the limiting reagent as well. So what is the mass of marble? 50 grams. What is the concentration of acid? 1 mole. We have 100 cm cube. So number of moles of acid we have is 0.100 moles. This is volume times concentration. The volume is in cm cube. The con is in dm cube. So you must divide by 1000 to convert the cm cube into dm cube first. So we get 0.100 moles of acid. Number of moles of marble used is mass divided by molar mass. This is the molar mass of calcium carbonate, and we have 0.500. And because we see that 1 mole of calcium carbonate is equivalent to 2 moles of HCl, it means that the acid is the limiting reagent. So how do we determine that the acid is the limiting reagent? If we have 0.100 mole of acid, 0.100 mole of acid, it will react with 0.0500 mole of marble or calcium carbonate. But in fact, we have 0.500 moles of marble. So this means that the marble is in excess and the acid is the limiting reagent. So with this, we will be able to know what is the volume of carbon dioxide formed, because 0.100 mole of acid will give me 0.0500 mole of carbon dioxide. I divide by 2. This is the number of moles of carbon dioxide. Why? Because 2HCl is equivalent to 1 CO2. So 2 is to 1, 0.1 is to 0.05. So number of moles of carbon dioxide multiplied by 24 for RTP, and we get 1.2 dm cube of CO2 produced. So when we draw the graph, take note, 1.2 dm cube of gas produced, this is in cm cube. We convert this by multiplying by 1000, we get 1200 cm cube of gas produced. And with the marble chips, we will expect a faster reaction than the one with the single piece of marble. So the gradient for the graph is steeper, it hits the plateau faster, and the volume of gas evolved in both cases will be the same. Because we use 50 grams in both cases, just that one is a single huge piece and one are small little marble chips. So they must be at the same level. And what is the volume of this level? It is 1200 cm cube. The next factor which affects the speed of reaction is the pressure. If we change the pressure of a reaction mixture, we may be able to change the speed of reaction. But take note, this doesn't apply for every single reaction mixture, only particular ones. So let's take a closer look. So what happens when we increase the pressure? So in container A, assuming we have a gas in container A, we have two gases in container A, and we have the same two gases in container B. When I compress the gas in container B, you notice that what I've changed is simply the volume that the gas occupies. So volume A versus volume B. Volume B will be less than volume A. So what I have indirectly done is to increase the concentration of the particles of the gas. So I've brought the particles closer together, and because they are closer together, it means that there are more reactant particles per unit volume, and it also means that there's a higher chance for collision to take place. So I've increased the probability of collisions taking place, and as a result, I've increased the probability of them colliding with sufficient energy to overcome activation energy and colliding with the correct orientation. So effectively, I've increased the frequency of effective collisions, and as a result, the speed of the reaction will increase. So to lead on from here, if I were to have a reaction mixture containing, let's say, H2SO4 plus NaOH, is there a way for me to increase the speed of reaction? Na2 plus H2O, is there a way for me to increase the speed of reaction by increasing the pressure? No, this is not possible. Why? Because they are all in aqueous state. So being in a aqueous state, it means that it is already very closely packed, slightly disorderly, but already very closely packed. So there's no way for me to increase the pressure and result in the particles becoming even more closely packed. So this is compared to one which contains gases. Because gases, the particles are very far apart. Increasing pressure will bring the particles closer together. So the factor where we increase the pressure only works. It only works for gases. Only works for reaction involving gases, one of which is the Haber process. So N2 gas reacts with H2 gas in the presence of a catalyst 450-250 atm to give me ammonia. So if I were to increase the pressure, I will increase the rate of reaction. So that's why you notice that the pressure here is pretty much way above what is normal. Normal pressure is 1 atm. This is one atmosphere pressure. This is at 250, is 250 times that above atmospheric pressure. So increasing pressure will allow me to bring the reactant particles closer together. This increases the frequency of collisions, and it increases the frequency of effective collisions, and as a result my rate of reaction increases. The next factor which affects the speed of reaction is temperature. So if you recall the earlier equation, the Haber process, why is the temperature at 450 degrees Celsius? Why? Or as a matter of fact, you would have heard before of people heating stuff to make the reaction go faster, one of which is the cooking of food. So why does food cook faster when it is in a closed container? When it is in a closed container and when the temperature is very high in the container. So why does it cook faster when the temperature is higher? So once again, it brings us back to the collision theory. So when particles collide, remember they must collide with sufficient energy to overcome activation energy. So when I increase the temperature, my particles gain kinetic energy. They gain Ke. They move faster. More energy, they move faster. This means that because they move faster, they are more likely to collide. And when they collide, because they have more energy now, it means that there's a higher chance of them having enough energy to overcome activation energy. So as a result of this, it increases the frequency of effective collision, and the speed of the chemical reaction will increase. Simple? Right, so now let's move on to checkpoint 3. So you can pause the video now to attempt the checkpoint, continue the video once you are done. So let's analyze checkpoint 3 together. You notice that there are A, B, C, D, 4 beakers with marble powder or marble chips and some acid. So this is a calcium carbonate reacting with acid reaction. In which beaker will the reaction be fastest? So let's take a quick look first. This is marble powder, marble chips, marble powder. So instantly we have eliminated B and C, because being marble chips, they would have a smaller surface area to volume ratio. The reaction will be slower. So now we are left with options A and D. So in option A, we have marble powder, 200 cm cube of 3 mole per dm cube acid. Over here we have the same mass of marble powder, the same volume of acid, but a lower concentration. Temperature wise, 20 degrees versus 30 degrees, this is a higher temperature. So in the first beaker, we have a higher temperature and we have a higher concentration. So it means that in the first beaker, we will have the fastest rate of reaction. Answer will be A. The last factor which we'll be discussing is the presence of a catalyst. A catalyst can help to speed up a chemical reaction, but how does it do it? So let's go on to the definition of a catalyst first, which is a substance to increase the speed of a reaction, but remains chemically unchanged at the end of the reaction. So if I put catalyst A into a reaction mixture, at the end of the day, when I clean everything up and I purify and I extract, I will be able to get back my catalyst A. So based on this premise, you would be able to guess that I do not need to add a lot of catalyst for reaction into a reaction mixture, because the catalyst itself remains chemically unchanged, so it can continuously catalyze a reaction. But how does a catalyst work? So let's take a look at this very simple energy profile diagram over here. So over here we see two reactions. We see two graphs, 1 and 2. We see graphs 1 and graphs 2. And we know that these two are activation energies. So we can see that the EA for 1 is lower than that of 2. Okay, this is the reactants, this is the products. One belongs to a catalyzed reaction, 2 belongs to an uncatalyzed reaction. So based on this energy profile diagram, I can say that a catalyst increases the speed of a chemical reaction by providing an alternative pathway with a lower activation energy for the reaction to proceed. Take note, it provides an alternative pathway. It does not lower the activation energy of the reaction. The activation energy of the reaction will forever stay the same. This is an alternative pathway. It's a totally different pathway from the first reaction, from the first uncatalyzed reaction profile. And this alternative pathway has a lower activation energy. Okay, so because it has a lower activation energy, it means that more particles now, when they collide, they will have enough energy to overcome the lower activation energy and react to form your products. So there are some characteristics associated with a catalyst. This one I mentioned earlier, we only need a small amount because it remains chemically unchanged. So for example, if I were to catalyze the breakdown of hydrogen peroxide into water and oxygen gas, I will use the catalyst MnO2. So I just simply need to add a little bit of MnO2 and the reaction will proceed and proceed and proceed because the catalyst remains chemically unchanged. Next, it is not used up during a chemical reaction. If it is chemically unchanged, it means that at the end of the day, I can obtain back the catalyst. So this is the same as saying that it is not used up during the chemical reaction. A catalyst is also specific. It is selective, and different reactions require different catalysts. So take for example this equation here, the breakdown of hydrogen peroxide into water and oxygen catalyzed by MnO2. If I were to add in, say for example, a lump of iron, it probably wouldn't catalyze the reaction. The reaction will still proceed at the same rate. So from this we can see that catalyst is specific and selective, and we need to change the catalyst for different reactions. So in our body for example, in the mouth we have amylase. Amylase breaks down your carbohydrates into a simpler form of sugars. In your stomach, to break down your proteins, you have pepsin. So these are different catalysts, different biological catalysts. They are used for different purposes to break down different materials. A catalyst increases the speed of a reaction but does not increase the yield of a reaction. So what it does is simply make the reaction go faster. It doesn't give you more product, because how much product you have it depends on how much reactants you put in the first place. So it makes a reaction go faster. You get the same amount of product but in a shorter period of time. So if you were to link this to the industry, this would be actually very good, because if I can make more product in a shorter period of time, it means that if in the same time duration I can make a lot more product. So by making more product, it means that I can sell it off for more money. So in industry, catalysts are always used to speed up reaction when it can, because more product equals to more money for the company. A catalyst can be poisoned by impurities. So poison means that it can no longer act as a catalyst. So for example, platinum catalysts are easily poisoned by impurities. So when it is poisoned, it can no longer behave like a catalyst. So how is a catalyst actually poisoned? So let's imagine that this is a catalyst. This is the surface of a catalyst, and the reactant particles come on board here. Let's say this is a reactant particle. This is a reactant particle, and it comes on board here. It comes on board, and it must plug into the side. So in order for the reactant particles to plug into the side must be clean. So if let's say I were to have impurities that block the site, when my reactant particles come along, they will not be able to bind to the catalyst. So as a result of this, the catalyst no longer functions, and we say that it has been poisoned. The last point here is not really a characteristic of a catalyst, but more about nature of catalysts. So most catalysts are usually transition metals, or they are compounds. So why is this so? Because if you recall the picture I drew earlier, for a particle for something to behave like a catalyst, it must be able to bind to the reactant
particles first. So transition metals have many electrons. They have many electron shells and many orbitals. Some of them are d orbitals. This is in A levels, you'll learn more about this. And the d orbitals are usually empty or not fully occupied by electrons. And because they are empty and not fully occupied by electrons, the reactant particles can actually donate their electrons into the d orbitals to form a temporary bond, which actually holds them together here. So when they're held together, there's an increased chance for them to react to give you the product. So transition metals, being elements with d orbitals and sometimes unfilled d orbitals, can behave like a catalyst. Right. We move on to another example of a catalyst, but in this case, a biological catalyst. So I'm not very sure whether you have seen before enzyme soap, but an enzyme is actually a biological catalyst. So the enzymes in the soap help to break down substances. For example, because it is in soap, you would presume that it will help break down proteins from food stains on your shirt, or maybe it breaks down some of the fats that could possibly stain your shirt, and effectively it helps to make your cleaning job a whole lot easier without using any harmful chemical compounds, which would be bad for the fabric of your shirt as well as bad for the environment. So let's go on to the definition of a catalyst. It is the definition of an enzyme. It is a biological catalyst. So being a catalyst, it will also increase the speed of a reaction and remain chemically unchanged at the end of the reaction. So these two factors at the back remain the same. The only different thing is that it is a biological compound. So being biological, it means that they are usually made of proteins, and they are substrate specific. This basically means that they are selective, so they do not catalyze every single reaction in the world. As I mentioned earlier, amylase breaks down carbohydrates, and your pepsin breaks down proteins. If you switch them around, the reaction will not take place. And being biological, they are also sensitive to temperature changes. So why are they sensitive to temperature changes? A very quick explanation. So for an enzyme to work, let's say I draw this as a simple enzyme. So this is the enzyme, looks like Pac-Man, and this is the substrate, or this is the reactant substrate. Right? So when the substrate enters the enzyme reaction happens and it releases the products, it releases the substance, the substrate, as the products. So this site here is what we call the active site. So how does the active site come about? How does it come about? It is because of the configuration of the protein. It may be the tertiary structure, it may even be the quaternary structure. So the protein that makes up the enzyme has a structure like this. So this is the helical structure. So this is the first structure it has is the long chain structure formed by the amino acids. Then amino acids can curl up to form a helical structure. This helical structure can further curl up itself to give you the tertiary structure, primary, secondary, tertiary structure. So when it curls up like this, you notice that there's an opening here, and this opening here corresponds to the active site. So how does this protein, how does this polypeptide chain, this protein chain here curl up? It's because of interactions or electrostatic forces or attraction between the amino acids. So some of this could be hydrogen bonds, some of this could be weak permanent dipole-dipole interactions, basically weak forces which hold them into the secondary structure, and weak forces which call them into the tertiary structure to give you this active site. So because this tertiary structure is held together by weak bonds, when I increase the temperature, I will increase the Ke of the enzyme. So the enzyme will move faster. So if it moves faster, it means that it will vibrate really, really fast. And if it vibrates really, really fast, it means that there's a higher chance of the bonds that hold its structure together from being broken. So once they are broken and it uncurls out and it unfurls out, the active site is lost and it can no longer behave like a enzyme or catalyst. So they are sensitive to temperature changes. And as a result, because they are made of proteins, most of them, they function most effectively within a narrow range of temperatures, and generally this is about body temperature, and with every 10 degrees increase in temperature, the rate doubles until the enzyme is denatured. When we say that the enzyme is denatured, it means that it can no longer behave like a catalyst because it probably has lost the active site, the configuration of the active site. Similarly, enzymes are also sensitive to pH changes. So why pH changes? Same as the explanation for temperature changes, is because the enzyme is held together by weak forces. The active site, the configuration of the active site comes about because of weak forces holding the enzyme, holding the polypeptide chain in its tertiary configuration. So these forces arise because of charge groups, and the charges of the groups will change based on the pH. So when the pH changes, when it fluctuates wildly, the charge groups will change. So that if the charge group loses a charge and the weak bond is formed between the positive and negative charge, and the positive charge now loses itself, it becomes neutral, this bond will be broken. So when the bond is broken, the active site, the configuration of the active site is lost and it can no longer function as a catalyst. So enzymes are sensitive to pH changes and they function within a very narrow range of pH. Now let's move on to checkpoint 4. So pause the video here and attempt the checkpoint. Continue with the video once you are done. In checkpoint 4, we see that we have a little graph here involving a react which tells us how fast the hydrogen peroxide mixture here decomposes. So as it decomposes, it gives us water, H2O2 peroxide. It gives us water plus oxygen gas. So let's balance the equation. There should be a half here. So we can collect the O2 gas that is evolved against time, and we will be able to determine what is the rate of the reaction. And you notice that at the beginning, this is really, really slow. The gradient is really, really low until about 5 minutes when a black solid was added and the rate shot up. The gradient increased tremendously. So this gradient is here, really almost flat. This gradient is all the way up, and eventually it becomes 0 here. So what is the black solid that was added to the solution at 5 minutes? This is a catalyst. And what is the catalyst? It is manganese 4 oxide, MnO2. So this is a very common catalyst for the decomposition of hydrogen peroxide into water and oxygen. So what is the equation for the decomposition of hydrogen peroxide? It is H2O2 breaking down to H2O plus O2. It is okay to write liquid or aqueous for this because hydrogen peroxide is sometimes purchased or stored in the aqueous state. That means it is diluted with water, because by itself it is pretty unstable and the reaction can get really vigorous. The next part is to calculate the maximum volume of O2 evolved at RTP. We have 1.7 grams of hydrogen peroxide in the absence of the black solid. So based on the earlier equation here, H2O2, H2 and O2, we can first calculate the number of moles of hydrogen peroxide. So this is a simple mass divided by the molar mass of H2O2, and we have 0.0500 moles. So this is a 2:1. 2:1. 2 H2O2 is equivalent to 1 O2. So 2:1, it means that 0.05 moles of hydrogen peroxide will give me 0.0250 moles of oxygen. It is half, 2:1. So to find the volume, I multiply by 24. 24, why? Because it is at RTP, and we get 0.600 dm cube of O2 produced in the absence of the black solid. So now when I add the black solid, which is the catalyst, or MnO2 in this case, what is the volume of O2 that will be evolved? It will remain the same. Why? Because the volume of O2 evolved only depends on how much reactant we have initially, which is 1.7 grams of hydrogen peroxide. So if I have 1.7 grams of hydrogen peroxide, I will have 0.0250 moles of O2 produced, and as a result, I will have 0.600 dm cube of oxygen gas. There will be no change. And now, if I were to draw an energy profile diagram to show the energy changes with and without the black solid, which is the catalyst, I will be able to draw something which looks like this. So this is the reactants. In this case, it is H2O2, and this is the product, which is H2O plus O2. Balance this equation. This is an exothermic reaction, so it goes downwards. So the first energy profile belongs to the reaction without the black solid, so EA will be much higher. So this is the EA for the uncatalyzed reaction. Uncatalyzed reaction. So when the reaction is catalyzed with the black solid, or the MnO2, I will have a lower EA. So this is the definition of a catalyst. It provides an alternative pathway of lower activation energy for the reaction to proceed. So imagine yourself going up a mountain, or going through the tunnel in the mountain. You get to the same place as usual. The reactants still become the products. H2O2 still becomes H2O plus half O2 plus O2 over here, but the reaction is much easier to proceed, so it goes much faster. So we have come to the end of the topic on speed of reaction. So practice your tutorials and practice the various worksheets given to you, and I'll see you in the next lecture. Thank you.